Hi all, I'd like to walk through problem 7.24 and 7.26 from chapter 7.3 using Excel. So we're basically going to do a difference of means test, and most of this is the same as what we've done before. The one major change is that we have our standard error is equal to this expression. So the standard error is equal to the square root of our standard deviation squared divided by our sample size plus the standard deviation of the other sample squared divided by that sample size. Our degrees of freedom is just going to be based on whatever sample size is smaller. In 7.4, both the sample sizes are the same. So here is 7.4. Let's go ahead and go down to 7.4 here. Okay, let's read the problem. 7.24, diamonds part 1. The prices of diamonds are determined by what is known as the 4 C's. The prices of diamonds go up as the carat weight increases, but if you look at a 0.99 carat diamond and a 1 carat diamond, the 1 carat diamond is much more expensive. Even though they're like almost the same size and nobody could actually tell the difference. So we have two random samples of 0.99 and 1 carats. And here, so we have a whole bunch of 0.99 carats, and these are the mean prices. It's not the mean price total, obviously, right? You can't get a 1 carat diamond for $56. It's divided by, it's the mean average price divided by 100 for this one, and then the mean average price divided by 99 for this one. That doesn't matter too much because we have our sample statistics here, and we can just use these numbers. Okay, I've copied this table over here. This is for the 0.99 carats and the 1 carat. The mean is 44. The standard deviation of this sample is 13. And then the sample size is 23. And the mean is 56. And the standard deviation is 16. And the sample size is also 23 for the 1 carat. We have our null hypothesis is that the two means are the same. So that these prices are actually the same. They're obviously not the same here, but they are the same on average if we have different samples, or the alternative hypothesis is that they're different. This problem is kind of funny because it actually tells us right here, like in the second line, that they're going to be different, right? It says, what does it say? It says, for example, the difference between size of 0.99 carats and 1 carat diamond is undetectable to the human eye, but the price of 1 carat tends to be much higher than the price of 0.99 carats. So this sentence right here tells us that the null hypothesis is not going to be true. But we can't just finish. We'll actually go through the whole hypothesis test. So our null hypothesis is that the two means are equal. The alternative is that they're not equal. A different way of thinking about our null and alternative hypothesis are, if they actually are equal, it means that if you take one and you subtract the other, they should be 0, right? And if they're not equal, that means if you take one mean and you subtract the other mean, they will not be equal to 0. So these are the exact same thing as this. It's just a different way of phrasing it. But this is how we actually think about our test statistic. With our test statistic, we take our sample mean 1 and subtract off the sample mean 2, and we compare it to the mean that we would expect. We would expect it to be 0, right? We'd expect that the difference between these two prices, because it's undetectable to a human eye, would be 0. And then we're going to take that and divide it by our standard error. So this is how we compute our test statistic. I went ahead and did that here. Oh, let's go back to the standard error. The standard error, we use that formula that I showed before. Let me pull that back up. Obviously these are not going to be the population standard deviations. We will use the sample standard deviations, and later on in the chapter it shows us this. We can do that. So our sample standard deviation is this number. We're going to square that. We divide by this, our sample size. And then we add that to this number, we square that, and we divide by sample size with this. So this is the expression in Excel that does that for us. So we're taking the square root of all of that stuff. So this is our standard error. So now we compute our test statistic. So the difference of the means, minus 0, because we're expecting the difference to be 0. That's our null hypothesis, divided by our standard error. If we want, we can do this hypothesis test with a critical number. So I'm doing my critical number here. It doesn't give me an alpha, so I'll say alpha is 0.05. It doesn't give me an alpha in this problem, or a significance level. So I'm going to go ahead and use I'll find my critical number in two ways. I'll do it here using Excel, and I'll also go ahead and do it with the t-table. So I want the alpha to be 0.05. I know I've got 22 degrees of freedom because their sample size are both 23. And this is a cool Excel formula. It actually tells us for the 2t, so it's taking the 0.05 and splitting that in half. If we look at, let's look at a generic t-score graph. So it's saying that this side is 0.05, or sorry, this side is 0.025, or 2.5%, and this side is 2.5% also. We can also just get our critical number if we go down to 22 degrees of freedom, which is right here, and we want the alpha in the two tails to be 0.05. So we have 2.7 there, and in this one we get the same, we get 2.7, or 2.07, sorry, 2.07. So either way you want to do it should be fine, except for those pesky problems where they want you to round up to 4 decimal places. All right, so what we would do here is we would say, oh, our test statistic is much larger than our critical number, so we would reject the null hypothesis, meaning that the average prices of both these things are not the same. We could also do it with the p-value, so I'm going to do it with the p-value here. I got t.distribution.2t's, 2t distribution. E8 is my test statistic, so it's my test statistic here, and I've got 22 degrees of freedom, and it spits out my p-value. It's 0.009, which is much less than our alpha, so we would once again reject our null hypothesis. We haven't really been doing this too much in class. In fact, a student pointed out to me that we could do this, which is really great. The way we've been doing it in class is we go here, we do t.distribution, we have our test statistic, 22 degrees of freedom, true, which gives us this, which is the value less than our test statistic. But then we have to do 1 minus our test statistic and then multiply it by 2 because it's a two-tailed test. And we get the same number either way. So this way, it's much faster. Anyway, so now we would be done, right? We would reject the null hypothesis. We would say that they are not actually the same. Let's do problem 7.26. 7.26 is the same numbers, diamonds part 2, except for now we're making a 95% confidence interval. Same data here. So we have to do the difference of means, so that's this number minus that number, times our t-score value, which we actually just found is our critical number here, right? Times our standard error, and standard error is that number right there. So our t-score value, we're making a 95% confidence interval. That means that in the two tails there are 5% of the, in the two tails represent 5%. So 95% in the middle, if we're going back to our table. Once again, this part in the middle, right, this is 95%. This is 0.25, and this is, sorry, 2.5, and this is 2.5 over here. Anyway, so we can just compute this, plug this whole thing into Excel. So I've got my difference of means. I've got my inverse t function with two tails. So I've got my 5% here, my degrees of freedom, which is 22, and then I'm going to multiply it by my standard error. I do the exact same expression over here, except for now I'm doing the plus instead of minus. So we're 95% confident that the difference in the means is between negative $21 per hundredth of a carat or negative 3. So we're 95% confident it's in between those two. All right, and that is how we go about doing a 2-sample mean t-test. Difference of 2 sample mean t-test. Let me know if you have any questions. Thanks.